So problem 27, now we're going to be looking for some magical integer m, such that no matter what element you give me, a to the m always equals e. We're going to have our group axioms here, and then the key to this problem is going to be problem 26. So check that problem out. What problem 26 says is a to the n equals e for some n. The reason why n does not work for problem 27 is that this n only works for a, or maybe some small set of the group, but probably not the whole group. Now we want to look for a new number called m, such that no matter what element you give me, a to the m always equals e. So let's look at that. First, let's look at two elements. So here I'm calling them a and b. We know from problem 26 that these exponents exist. All these underlined equations are saying is that there is, for a number of times that we can multiply it by itself to get back to the identity element. And the same thing for b. So those numbers just might not be the same. So the question is, how do we combine j and k to find something that such that a to that power and b to that power gets us back to e? And it's pretty clear that what we saw with the symmetric group is a good hint here. So if a to the jk, the product of these two, what can we say about that? Well, using exponent rules, that's a to the j to the power of k, which is just a to the j times itself k times, right? This is where it's important to remember this shorthand for a to the power of something. Remember, a to the j is just an element, so an element to the power k is just the element repeated k times. But we know, based on our previous problem, that a to the j equals e, and e to any power is always going to equal e. So we found an exponent such that a to the j equals e, and the exact same analysis works for b to the power of jk as well. And so what we've seen is that if we take two elements, the product of their magical exponent is going to work. It gets us back to where we want. And now the question is, how do we expand this to the rest of the group, right? All we know about the group is that it's finite, and that every element from problem 26 has its magical exponent such that we get back to e. So what we want to do here is take this idea and combine it with what we did with a and b up here. And if we take the product of all of these n sub i's, so every element has its particular exponent that gets it back to e, let's let m equal the product of all of those exponents, okay? And what happens is, here ai is any element that you want in the group. Given any element, its magical exponent lives in here. It's a factor, right? So m contains this the power that we want. And the idea is we're going to take an a to the I, and instead of taking it to the power of m, we're going to take it to the magical exponent, and we're just going to repeat that process m times. So what this really looks like is ai to the power of ni, not to the power of m, but we factored out the n sub I. And that's what this right-hand side here is looking at. So a to the I to the power of m, we can factor out an n to the I, and then what we're doing is we're repeating this a certain amount of times. And how many times we're repeating it is actually m divided by n sub I, which we know is an integer because of how we built m. M has a factor of every n sub I in it. So it doesn't matter which element you take, the way we built m makes sure that we end up with this. We end up with e repeated a certain amount of times, which is always going to be e. Thanks for watching this video. I hope you enjoyed it. Make sure to subscribe so you don't miss out on future videos. And if you have a question about this problem, or if you'd like to request a solution to a different problem you're working on, let me know in a comment below.